Good afternoon, everyone. So we will earlier, like we discussed, how to write or formulate the optimization problem, and then how we can write the code for the optimization problem with the help of MATLAB. So there are like we discussed one like very simple fundamental program that we can also write it for ourselves, and we can also use the inbuilt tools available in MATLAB. So now I will try to focus on so far, like we tried to solve the linear problems and quadratic problem. So that function we have used earlier. Now if we go to the like ACOPF problem. So let me share my screen. So if we look at the ACOPF problem, so this ACOPF problem is very much non-linear. So here you can see that the very first equation is quadratic in the nature. It can be linear, but the second equation, which is active power balance at the nodes, is highly non-linear. Third equation, which is also the reactive power balance, it is also non-linear. Then third and fourth are basically like these powerful limits are there. Fourth equation. Fifth is powerful limit, so that is also a non-linear sort of equation. Then we have voltage and angle limit, so that those will go into the lower bound or upper bound. Okay, so how the F min cone works. So let's talk about that. That is, so most of our problems are basically of non-linear nature, and they need extensive basically declaration, and like we have to define them in such a way that in terms of like MATLAB and matrices we have to define it. But the thing is, like with F-min cone, it's very robust, and we can develop our own algorithms on the with the help of the F-min cone. So F-min cone we can use like solving a part of equations, and then try to get the use or try to use this particular function to solve our own dedicated problems, which we are facing in our research. So I have already, written this particular code, and I will just explain it to you because it's a bit, lengthier as compared to what we have, written so far. So here I'm basically looking at a, five bus system, and in this particular system, like we are in this particular line, we are trying basically loading this particular case. So whatever is the case, it whether it can be 5 bus system or a 6 bus system, or 14 bus IEEE system. So any system case we can load from here, and this load case command will be available from the mat power. So if you try to run, I will share this code. So if you try to run this code, you have to install mat power in or basically embed the mat power in your MATLAB software. So otherwise this load case command will not work. Otherwise apart from this, in casing, or basically entering this case file, you can what you can do is like you can open this particular file, and you can copy paste these matrices. This is like the case files only have the data, so you can copy paste it here, then you don't need this command as well. Rest of the code is very much generalized. I will show you some of the like MATLAB. So mat power, so this command is mat power. Okay, I will mention which commands are from the MatPower, so that those things you have to you can work around if you don't have not able to install the MatPower. So we tried to the very first line is loading of the case 5. Once we have loaded it, as explained earlier today morning, that all the information or all the powers should be in per unit. So this is what we have done here in the line number 6. If you see, this is the like bus data, and it is divided by the base MVA, and the 3 and 4th column is basically divided by the base MVA. So the third and fourth column gives the information about the active and reactive power demand, and that was given in megawatt and MVAR. So that's why we have converted that into per unit. Then the next information which needs to be converted into per unit was the active and reactive power output of the generator. So that is variable, but the limits of active and reactive power output we can basically we have to convert that into per unit itself. So that is available in dt.gen, uh, basically in data matrix. And here the fourth and fifth column represents the minimum and maximum limit on the reactive power, and ninth and tenth represents the maximum and minimum limit on the active power. So basically, what this is what we are doing, that whatever is the maximum limits, which are either in megawatts or basically MVR, that has been converted into per unit. Once we have done it, we will look for the you know, like gather the information out of the whatever load case has been provided. So whatever is the case has been provided, that out of those case data, we have to gather the information. So line number 8 is basically, if you see, it is identifying the number of nodes or buses. So whatever is the size of bus matrix, so this dt dot bus matrix, number of rows will be equals to number of lines. So this is we are trying to solve. Then we are basically trying to identify the number of generators, then number of lines as well. So once we have identified these, and I have kept, like, instead of dt dot bus, I would like to use bus. So I have created some new matrices and with the same data. So bus represents the bus data, gen represents the gen data, similarly gen post and branch data. So these four are simply uh, the same data which are available in our case file. So like this data, all these four matrices are basically taken out and placed here in bus, gen and gen post and branch data. This then if you see here, like to write this non-linear terms like power flow between I and J, we have to basically uh, provide this particular we need this particular information, and this Yij and theta ij are basically the elements of Y bus uh, and the angles of the Y bus element. So this is like magnitude of Ij element of Y bus, and theta ij is the angle of Ij elements of Y bus. So we need to build a Y bus. So here again I have used a mat power command. So this make Y bus function is from the mat power, and if we don't have this, it will hardly take 5 or 6 line of new line of code by which you can make a Y bus matrix as well. So you can build your own function for that as well. So like and it does not it is not necessary that you have to install MatPower. I just recommend that it is very easier to work with MatPower. So uh, these are the two different basically commands I have used from the MatPower, which is line number 5 and 50. Okay. Now, if you look at this, our objective function. So this is my objective function where some uh, post we are minimizing, some constraints are there, and then so first of all, what is important here is like what we have to identify first of all is what is x, like by what are the decision variables by which we are minimizing this particular part. So this part we have already discussed that these are the different x available to us, like pg, qg, voltage and angle. So these are the different variables available to us. Now first of all we have to define those variables. Okay, so we have to provide like first of all how many number of variables, and once we have identified that, we have to be aware that which index in the x matrix represents which variable. So that is very important. Otherwise, if we are not aware about it, sometimes what happens that we will, instead of using like multiplying with the voltage vi, we can multiply with the power. So that notation we have to fix. So first of all we have to define the voltages. uh, each and every one basically can define these variables as per their programming logic. Usually, what I prefer is keep the constant terms up front and then variable terms in the end. And by mean constant is like for any n bus system, the variables which will be always throughout the different cases, the angles and voltage will always be equals to the size of the network. So if n bus system is there, n number of angles and n number of voltages will always be there. But generators are varying. Sometimes in 5 bus system we have 5 generators. In 6 bus system we only have 3 generators. So those generators are basically varying frequently. So that's why I kept. So this is how I have defined the variables. Angles and voltages are always have are fixed to the size of the network, and pg and qg are basically varying with the case to case basis. So that's why I kept angles as a in the sequence of the variables will be like angles in the very first, then voltages, and then pg and then qg. So then once I have used these variables, I have defined some upper and lower bound on all of these variables. So you can see this is upper and lower bound and some initial x naught as well. So if a n bus system is there, so we would try to keep this entire program as generic as possible. So if you see here, um, if a n bus system is there, the angles will be n, then voltages will also be n, and then pg and qg will know. So let's define first of all the x naught. Okay, so I'm trying to define the x naught, and x naught is the x size will be basically uh, so the size of this particular variables, like if I put it here, uh, overall size of number of variables, or I can simply say the number of overall number of variables will be, so n numbers of angles plus n number of voltages plus ng number of pgs plus ng number of qgs. So this will be the actual size of the variable. So this is what we have defined here. Like in the initial x naught, you can see I have defined zeros. So 1 by n. So n zeros I have defined. Then I have defined voltages generally we keep at 1 per unit. So that is has been defined 1, and then plus 1 into ones of, and the size of the matrix is 1 by n. So n number of ones has been defined. Then there will be ng number of power active power generation and ng number of reactive power generation. So that I have defined here like 0. So all the power outputs I kept at 0 value. So that's why like angle is 0, then voltage magnitude is 1, and then power outputs are 0. Now let's put the upper bound. So we all know that the upper bound will be pi. So I have defined like pi into once 1 by n. So 1 by n times of pi has been defined. Then the maximum value of the voltage. So that information is available in the bus data. If you look at the bus data, the last and second last column represent the maximum and minimum value of the voltage. Okay, so this has been identified. So I will use the Vmax from here. So you can see that the bus data in from the bus data, I am using the 12th column. So that 12th column will give me the maximum value of, or whatever is the maximum voltage levels. So that was like generally 1.05, 1.07, and sometimes it is 1.1 as well. So those values will come here. Then if I go into the generated data, so ninth column gives us the maximum, as we discussed earlier in the morning as well. So ninth gives me the maximum and 10th column gives me the minimum. And similarly, fourth column gives me the maximum Q and fifth column gives me the minimum Q. So that has been defined here, like generated data ninth column will give me the maximum P, and generated data fourth column will give me the reactive power maximum limit. Okay. Similarly, the lower limit is like minus of pi. So that is for all the angles, n number of angles. Then the 13 column from the bus data gives me the minimum voltage level. So that is also taken. And then we know that the 10th column gives you the P min and fifth column gives me the reactive power minimum limits as well. So this is what we have defined so far. Here, so by defining these, let me copy paste this. So this part, let's copy it and put it in the MATLAB file so that we can work on it. So I will paste it here with ACOPF. Okay, and I will paste it here. Okay, so this part has been moved here. So if you look at this particular part, we were able to so we have defined the minimum voltage angle. So this part has been, so equation 6 has been defined with the LB less than equals to X less than equals to UB. So equation number, so this is defined by equation number 6, equation number 7, and then we have some equations like okay, I have repeated 3 number of equations. So let's say 4A and 4B. So equation number 4A, equation number 4A, and equation number 4B. So these LB and UB which we have defined, they caters these 4 number of equations. So so far it is good. Then if you look at the syntax of the fmin conf function, so we are going to use fmin conf function for this one. So this is our fmin conf function, and if you look at the syntax, it needs certain input or basically input entries. So this is my fmin conf function. So this, like, MATLAB understand this function itself. So here, this is a generalized formulation provided. Here you can see that we are going to minimize certain function. That function can also be non-linear or linear, but we will consider that, okay, for f min cone these function has to be defined, and we will assume that it is a linear function. Okay, then if you see here is cx less than equals to 0. So this c and ceq are basically like two constants which are non-linear in the nature. So this cx and ceqx, they are considered as a non-linear equality and inequality constants, okay, in action code. Then rest of the three, I think we already discussed it earlier as well with the quad prog and lin prog, that this is our linear inequality constant, and the xeq, sorry, aeq dot x equals to beq is our linear equality constant, and lbub are the bounds on the variable. So this we have to supply, and there are, like in the syntax you can see there are multiple ways of supplying it. Like depending upon how much information you have, you can supply that information, and you can omit the rest of the basically uh, information. Okay, so this is what we are going to do here. Like this is my f min con, and I will supply all of these. Okay, so if I look at this particular function, you can see that yes, here. So some linear equality and inequality constants are there, but if you see the equation number 2 and 3 are non-linear, so they will go into ceq. So these are basically both 2 and 3 will be part of ceq x equals to 0. Then if I look at this has been defined already, and we have discussed that this will be basically lb and ub. Then we have defined that this equation will be cx less than equals to 0, because these are non-linear, but and they are um, inequality constants. Okay, so we will define it like this, and then these two are basically our again lb and ub, and the last equation is actually the linear equation, but either we can define it like aeq x equals to beq, but for the time being we will define it, instead of using this part, we will use that it is also a ceq. Okay, and we will define it like this. So as we can see that there is no equality or inequality linear constant, so I have defined those here in my program as a empty matrix. So like a is empty, b is empty, aeq and beq is also empty, so I have defined them empty. And then I'm just like I will define all of them, but I will call the function f min con, and certain options I have placed here, and just to see, like like this optim set is basically to set the optimization options. Okay, and those options are defined like opts, and optim set is the function which basically defines the different attributes of this function. You can simply like pressing f1 on this particular part, and you can know that what are the different inputs you can define. Like if you see here, certain tolerance can be defined, maximum number of iterations can be defined, maximum number of function evaluation can be defined. Okay, different checks, what else can be like displayed or not. So you can like make the display off. You can like see the each iteration or the final result or some notification. Okay, so these basically of everything is available, and it is also mentioned here that like which solvers can be used to use this particular function. So I have defined these as a just to see like how the options also work. So just to give you that quick example. Now here I have to like again look at the function. So the very first entry will be the objective function. Just like the quad probe or we used lin probe, we used to supply H and F in quad probe, the very first entry, and then we used to supply, I think, F in the lin probe as well. So the objective function will be supplied first of all. So this is how, like in this particular fmin code function, we are supplying the objective function, and that objective function is actually a function, and which has been made in some other .m file. So like I have made this particular file with the same name, okay, and then the same input arguments, and I have defined this here, but let's not go into there first of all. So this is the objective function. Then if you see, some initial gas has to be provided. So we have x naught has been provided, then a b aeq and beq. So like all of these ab and aeq beq are basically empty for this particular acopf case. So we have not like providing them, and we have defined them as a empty matrices. Then if you see like the next sequence will be the lower bound and upper bound. So with this particular variables, we had earlier defined line number 19 and 21. You see upper bound and lower bound as well. After this, we have to define some nonlinear constraints. So we have do have equality as well as inequality nonlinear constraints. So in this particular function, where its name I have given like sets underscore man NLC. So you can give it any name. So we will define our equality and inequality non-linear constraints in this particular function. Then I have provided the options which I have put. And once I run it, I will get the different outputs, like what is the x value, like variable values, what is the function value, what is the exit flag, output, lambda, and gradient and Hessian of this particular problem. Okay, so this grade and hash is basically gradient and Hessian of this particular problem. And then I have used certain lines after it. But let's go to the first function, which is main objective function. So this is my main objective function. In main objective function, I will supply the function with the variable x. So the variable x has been supplied here. Apart from that, I will need some other information, and those are basically like how many number of nodes are there, how many number of generators, and what are the cost coefficients, because in objective function only cost coefficients are present. Okay, so we are basically using this piece of code, and if you see here, like so this is the piece of code available to us, and you can see it. And here the objective function which we had was basically summation over I equals to 1 to n, and sum a p square plus bp plus c. Now, as explained earlier, that these A, B, and C are cost coefficients, and the units of A, B, and C is like A has dollar per megawatt square, B has dollar per megawatt hour, and third one is just simply dollar cost. So, and I also explained earlier today that the power output should be basically a per unit value. So we need to keep the power output at the basically per unit value, and if we are converting that power outputs in per unit, we have to convert these cost coefficients as well in the per unit. So if I'm using per unit, I will rewrite or reiterate myself that this a should be multiplied with whatever is the base mva square into p per unit square plus B into base MVA, okay, and then multiplied with the P per unit plus C. Okay, so this is going to be the objective function. So we have defined it here as well, like for I equals to 1 to number of generators. So for all the generators, we are basically trying to add these objectives in the zero value. So this is the objective is A P square plus BP. So you can see like this is nothing but the base value. So base value was 100. So base square is basically 10,000. So I have placed it here. This is 10,000 is nothing but the base square into A. So for any ith generator, A is basically available at the fifth location. If you see here, the gen cost data, it is 1, 2, 3, 4, and fifth location provides me A, then B, and then C. So I have defined it here in objective function that 1000 into ith fifth column, which give me the A into P square. Now what is P square? That is very important. So like the program which we have written here is basically we have to again look for the X. So X is basically delta 1 to delta n, V1 to Vn, and then P1 to PG, PNG number of generators, and then Q1 to QNG number of generators. So this is the X value, and I just have to like in objective function I do not have the angle values, I do not have the voltage value, and I do not have the reactive power value. So I need this indexing of the powers, and that can be obtained by simply like X variable, uh, the very first basically n number of variables, which is like number of nodes. So those n number of node is gives me the n number of variables in the system. So angles and voltage will have 2 into n value. So this is 2 into n plus the index of generator. So it is first generator and it's a 2n. So let's say 5 bus system. So 5 voltages, 5 angles, and the power generation will be at the 11th level. So this is what I have placed here, like 2 into nodes into plus 1. Okay, then the same value. So this is pi square, and similarly here you can see it's a B and P. Uh, if you see, I have also placed one more objective function below, and that objective function is for a linear cost function. So if instead of using, sometimes what happens that the cost functions are given in linear. So instead of AP square plus BP, the sometimes cost functions are like like some bid price, that okay, this much price I will charge for by the quantity. So in that case we will use the commented objective function, so we can use that as well. So this is my main objective here. The sequence should remain same like for any other programming language. uh, X node ng and cost should come here, and this is my main objective function. Now, if I go back here, then rest is basically like how the nonlinear constraints are basically defined. So this is my the nonlinear function. So I let me open this one. So this is our nonlinear objective function. Here I have some comments that some limits are there. Okay, the variables again just for the so that I do not make any mistake. I have placed that okay, this is how my variables are being defined. If you look at, let me get rid of this, just focus on the RF. So this we already understood earlier in the today's class that in a branch data I will find out like at how many places it is basically from node, and then at how many places it is the two node. Okay, so what we will do is we will use the same function find, but in the second column, not in the first column. So in the second column, if the ith number node is present or not, so this RF and RT will give me the connections, that how many connections are available for n node I. Then I have written if condition, like if R1 and so again the third is basically find the number of generators. So and what are their location. So this is basically the R1 will give you the location of those generators. Okay. Uh, Now, if this R1 is empty, it means on a particular node, there is no generator. So if you see here, like, if you see there are only three generators and we have six buses. So 456 does not have any generator. And if does not have any generator, this PGI will not come. Like, from the active power bank, this PGI is not even present there. So that's why we have identified that if it is empty, then I will not, write down the PGI. I will start from the demand point of view. And if that PGI like generator is available, then I will write down these equality constraints. So I have like, if and else conditions has been placed. Now, if you look at this particular line number 9, it is basically bus I comma 3. What will be the bus I comma 3? Can you answer it? Like from the bus data, third column, what will be the output? What it is basically? Anyone who wants to answer it? Like what will be this? What is bus I comma 3? Is it the ith generation output? I have a question for you. Is bus I comma 3 is generation of jth generator? So what in the bus matrix? So it is basically row I column 3 of the bus variable. So bus is not a variable; it's a matrix, and what column 3 represents in bus matrix? It's visible on the screen. Yes. So the third column represents the power, real power demand. So this is what basically we are writing here. So like if I look at this one, what I'm doing is I'm writing it like this. So I'm not using a for loop. I'm just simply using the matrix multiplication to write down this particular code. So if I look at this part, I can say that for any I, bus I comma 3 is basically PDI. This is PDI, and then plus X and I. So we have defined X like this. The very first is n number of angles, then n plus I. So ith voltage. So I can say it is VI. Okay, so this particular part is VI. Okay, this part is PDI. Then summation of x n plus 1 to 2n. So basically a summation of V1 to Vn. Okay, so what we are doing is um, we are making a sum, okay, of certain matrix, and that matrix is V1 to Vn. So it is basically V1 and 2 Vn, then dot multiplied with Y bus, and Y bus is basically ith column. So I 1 2 Y I n. So this is basically a vector in ith Y bus matrix. So if there's a matrix, ith row and nth column is basically used here. So we are dot multiplying with the this particular part, and yes, and absolute value is also there. So we are taking the absolute values of the Y bus, then dot multiply cosine of what theta ij, so theta I1 to theta I n. Okay, so this is Y bus angles, then minus xi plus x I2 x n. So generally we write it down like theta ij minus delta j plus delta I. This is how we are writing, used to write it, or other way around. You can see, so it is basically minus theta j plus delta I. So we are also writing it like this, that minus xi plus all the x, like all the other j. So it was summation over the j, and we are writing it like this. So delta I plus delta j, and we are trying to solve this particular part. So we will write it like this in the MATLAB as well. So you can see this is what I have written here. Any doubts? If you have any doubts. So second part is basically we are trying to write it down the same thing, but with you know um, generators as well. In some papers, I have read solving ACOPF is NP hard. Please explain the statement. It depends if some storage unit is used for ACOPF. If some storage is there, then the OPF will not be fixed to a particular time. So the ACOPF we solve. Okay, okay. Let me correct. There is a question in some papers I have read solving ACOPF is NP hard. Please explain the statement. So if there are a lot of combinations, the problem and like as being non-linear problem with many combinations, yes, it that problem will become NP hard. And if we have storage as well, like like we if we try to incorporate storage in ACOPF problem, then time complexity will also add. If, as far as like if we are not considering any like unit commitment related constraints here, which add that added complexity of the time, OPF can be solved for each hour separately. So this is what we are learning here. So in this particular part, the only issue is basically either we are going like the whether the problem will be convex or non-convex, and the solution we are getting whether it will be global optimal or local optimal solution. That is the only concern in this particular part. But if lot of combinations are there, and let's say we incorporate other constraints, yes, this problem sometimes become NP hard as well. And but so far, the only issue with our problem is that it is non-linear. But we can get the solution with the F-min code, and it is not NP hard. Okay, the existing one. Uh, just a second, I have to take a code. So another question is, what makes the OPF problem non-convex? Non-linear constraints basically. These non-linear constraints make the OPF problem non-convex. It depends, like what kind of other constraints we are using, and if I think we are aware what is convex and non-convex, but at transmission level, sometimes like with the relaxed conditions, we can consider it is convex. But if we write down the ACOPF with the like let's say for the distribution network where R is also part of it, the problem depends. Basically we have to look at the particular problem, like how it is been defined. But mostly if I write down the ACOPF problem with R plus JX in the transmission line, it may be non-convex, and most of the times the solution will be a local optima solution, and it won't be a global optima solution. So for that particular part, we generally go with the nature inspired algorithms to look for the global optimal solution. So whenever the problem is like, the nature inspired algorithm can find a solution from the non convex problems as well. So like so far we have discussed the conventional methods like interior point and all. So these gradient based method, Newton's method, and whatever the problems we have defined. So with the conventional optimization techniques, they are good with the if the solution space is convex, and if like contradictory objectives are not there. Okay, and if sometimes like whenever the mixed integers come, to some extent we can solve it, but in those directions basically the nature inspired algorithms are very good. But again, it is again trade-off between the speed, that they require a lot of uh, speed and computational time and computational burden as well. Okay, so If we look at this particular problem, what I have defined another equality constraint is if I have this part. So this first part gives you the PG. So earlier, like in our formulation, we have written it like this is PG minus PD, but I have defined it completely different. It's like PD minus PG, and rest of the part is like bring brought back on the one side. So that's why if you see here, I've used a minus sign with respect to the PG. So minus of the summation of the generators which are available on the first bus or ith bus. So that are the PGs, and this is basically the same is with the reactive power, the QG. So once this has been added to this particular CEQ function, then this term is the same as above, that it is PD plus Pij, like summation of the Pij. Okay, and so this is how I can define the my equations. I have to very much basically the only thing which we need to look here is proper indexing of the x. If x is not properly indexed, then what will happen that you wanted to multiply some variables and you will end up multiplying something else, because MATLAB does not understand that what is x in it. So you have to clearly define your x and use that definition, keep that definition in mind and use the definition to cite them or index those variables. Okay, so this with these two lines, like we can write that okay, our power balance equations has been placed. Coming up are basically like you can see there are only two lines which needs to write down the entire uh, n number of active and reactive power balance equations, but it is not that much simple. It is basically output of many iterations this logic was developed. If very fundamentally, if you are trying to write it down, uh, you will write down with the help of two or three four loops. You can use those loops instead of like simply using the matrices and the way I have used here. Okay, then the third one is basically like we have identified if the ith bus index is equals to 3, what we will do is we will create a angle equals to 0. So that is the this last equation represents that the reference angle should be equals to 0. Sometimes if you are writing this code, sometimes we have to keep the voltage as well, like uh, fix to a particular value. So this commented condition is like the voltage of the reference bus is like I have assumed 1.05, or it can be 1.0 or 1.1. So that value can be used here, but for the timing I have commented it. You can uncomment it. Okay, so this will is basically like defining all the equality and non inequality constants. So in this particular formulation, I have not used any inequality constants. So like if I open case 5, you can see this is my case 5, and there are limits on the first line and the last line of the 400 MVA. And but I'm not using that part in my nonlinear constants. I'm keeping that for you, and this is assignment for you, that you have to apply your own logic and add inequality powerful limits on line 1 2. Okay, so let's say the maximum power flow of line 1 2 is 300 megawatt, and what will be the output in that particular case? You have to remove this C equals to empty part for sure, because I am not using any line flow limit. So I have kept it as a empty, that okay, I don't have any inequality or no linear inequalities. So I have defined C equals to non-linear inequalities, and I have defined CEQ with this particular piece of code, few lines of the code. So let's see if this is working fine. Uh, Just a second. So if I run this particular program, uh, okay, so I have executed it, and let's see what are the different outputs. So I have basically, this is what we will get. So first of all, fmincon will run. It will take its course, and number of iterations are there. Some counts are there. Some fx values there. Some feasibility, and so whatever internally it is doing, it is showing that part here. So like I have used a command that display the iteration. Okay, so it is displaying iteration with detailed information. So whatever it is being solving, it is available here. So like it took 21 iterations to solve this particular value, and you can say like the then local minima is found, some optimization completed because the objective function is non-decreasing in the feasible direction. So you will get this kind of message. Uh, this message clearly says that local minima is found. It is fmincon is not certain whether the minima has been obtained from this particular for this particular problem is global minimum or local minimum. So that is the basically case with the non-linear optimization, that based upon the initial condition you will reach to the optimal point. Okay, so you may end up with a local minimum, and that everything will depends upon the initial starting point which we have defined here in X mode. Okay, so it is clearly written here that a local minimum was found that satisfies the all the constraints. So yes, we were able to found a minima. Minima is basically like the slope is zero at that particular point. Then it is also mentioned that objective function is now not decreasing any further. So we are trying to minimize objective function, so it is not decreasing any further, and some tolerance has been defined that okay, if objective function is stop decreasing to a particular tolerance, which is optimality tolerance. So we did not basically given user defined tolerance. Whatever is the default tolerance, we used it. Okay, so like this is how the optimality tool tolerance has been defined. So it is like just click it, you will can read it about it. Okay, then constraints are satisfied by the default value of the constraint tolerance as well. So like constraints are not uh, exactly balanced. You can say that they are balanced to some extent, and some tolerance was given. Let's say 10 to the power -4 or -6 is the tolerance. Okay, then after that, I had basically displayed all of these values, and here I have basically converted radian to degree. So the angle values has been converted to degree. I have converted the voltages, like the magnitudes. I kept it out. Power generation, so it was earlier in the per unit because we have to perform this code in per unit. So I have multiplied with the base just to convert exactly into the megawatt and MVAR. Okay, the QG. LMPs were also like dollars with per unit quantities. So I have divided that with the base MVA to convert that LMPs into dollars per megawatt hour, and the sum function value and the exit flag. So if you see here, we have obtained this solution. So this is my X solution. So this is how it looks like. So here you can see that 1, 2, 3, 4, and 5. This information is so how many buses we have? 5 buses we have. So this 5 bus information is what the 5 angles. So the first 5 are angles. Then in 5 bus, how many generators are present? So if I say in 5 bus system there are 5 generators, then 5 buses, and yes, so there are 5 generators. So if you look at the remaining 5, this is the voltages. So you can see, like, 3, 4 and 5, these are the 5 voltages, and you can see, like, many of the voltages are at maximum value, which is 1.1. Okay, so for 5 bus system, Vmax was 1.1. So this is also in per unit. Then 5 power active power output. So this is like zero point 0.4 is 40, and 1.7 is like multiplied with 100 should be 170, and so on, basically. So these are the 5 active power outputs, and these are 5 reactive power outputs. Okay, so this is the output we have. I have converted these initial 5 values which are available in the radian to the degree, like theta in the degrees. So these are the degree outputs. Then voltages, I have used the same value 0.4170 and multiplied it with the base. So these are the PG outputs, these are the QG outputs, and these are the lambda outputs. So I have, in, like, from the lambda you can see different lambdas are there, and we have solved this one. So we have equality nonlinear constants, and how many constants we had. So let's say if there are 14 bus system, how many equality constants or nonlinear constants will be there? If a 14 bus system is there, how many? Uh, so yes, 14 is there, so there will be 28 equations, uh, and those will be, like, one is for active power, another is for reactive power. This particular case we had how many 5 node system, so that's why we have 10 in non-linear um, equality constants. Though the delta reference equals to 0 is a linear equation, but we have defined that as a non-linear equation, like in the part of CEQ. So if you see this linear equation, we have defined in the non-linear sets. So these are basically like with this function file, we always define the non-linear, so that one extra constant is defined as a non-linear. So that's 11th constant is for the angle. So if you look at these values, you can see that some lambda or the dual variables are available here, and you can inspect those dual variables, like, what are the dual variables with respect to the lower limit. So most of them are very minimum. Then what are the different dual variables with the upper limit? So you can see uh, most of them are negative, but the sixth one is very high. Can you tell me why? This sixth and 10th value is very high. I'm not going into 11, 12, 15. So this sixth value and the 10th value is very high. Like rest of them are like 10 to power -7 and all. Why these values are like, why do we have these very high values? Anyone? The sixth one and the 10th one. What, first of all, the sixth and 10th, what does it signifies? So these are upper limits, right? किस चीज का upper limit है ये? Anyone? So these five values are very low, 10 to power minus 7. Then the sixth value is a high value, roughly around 148. So, like as compared to the other values, which are like 10 to power minus 7, I can say that it is very much high. Then seventh, eighth, and ninth is also 10 to power minus 5. So we can say that it is also negligible. But the tenth value is again very high, like 1.1 into 10 to power 3. So instead of 148, it is also very high. So why these values are very high? We have discussed this particular part earlier. Roshan, who wants to answer that? Any random guess? So incremental change in these variables have larger cost. That is one response. Anyone else, like in very simple language, if you want to understand this particular part? I explained you what the dual variable signifies. I explained that earlier. Hmm? So I explained you earlier as well that whenever optimization process have to put some efforts to keep a variable within the limits, this lambda value will go high. So if it is not putting any efforts, so which means that the lambdas are well within the bounds, then it does not have to put any extra penalty, then the dual variables will be zero or close to zero. Whenever the variables goes to either bound, whether it is higher or lower, then the process has to put basically extra efforts or put some force to make or restrict that particular variable to that limit, whether it is maximum limit or minimum limit. So we can say it signifies that like how much efforts is being placed by the optimization method. So if you see the six one, so like initial five were the upper bounds of the angle. So there was no angle limit violation. So that's why these are very much negligible and zero. Then 6, 7, 8, 9, 10th variables were, I think, the voltages. And if you see the sixth one is like V1 and 10th one is V5. And if you look at the output, the V1 is 1.1 and V5 is also 1.1. So they are actually at maximum value. So optimal, like they are, if the limit was not there, the value would have been more, okay, as compared to 1.1. So optimization is restricting these voltage value V1 and V5 to 1.1. So that's why we are getting some lambda on this particular limit. Now, if you look at the next five variables were PG, and if you look at the PGs, that these two are again like restricted to the maximum limit. Like if you see the data file, the maximum generator can produce is 40, 170, 520, 200, and 600. And by looking at this, I can simply say that these two are basically at the limits, whatever is the maximum limit. So I should get the variables of these two as a and non-negative as well. So 11 and 12th is also a large value for the dual variables with respect to P1 and P2 maximum limit. Then if you see 13, 14 and 15th are negligible because we are not putting any efforts. They are well within bounds. Then for reactive power as well, it is uh, up to 20. uh, Only 19 has some value and rest of the other are basically negligible. Let's see what is basically 19. So 19 is also at a limit of 150, so that's why it has a certain value. But we can, by looking at the dual variable, like it does not have very large value, it is some value as compared to like negligible, it has some significance. So optimization is like, this reactive power limit reached to 150, but even if I remove this 150 limit, it will hardly go maybe like 160 or 170. It will not go very much high. So optimization process is like we can say in like significance point of view, that putting less effort to keep this limit enforced. Okay, so by looking at the variables, you can uh, know this information. Then there are some LMPs are coming. Now the thing is, how can we verify these results? Okay, so I told you that there are inbuilt command in our MatPower. So I will use run OPF and let's say case 5, and okay, some syntax error. Okay, so I have ran this command, and let's see what are the different values. So once I have run it, it says that MetPower some version, ACOPF, ACOPF formulation, polar voltage and power balance equations. Interior point solver is being used, and if you see, like we also use the interior point solver. Like I have defined the algorithm should be interior point, so we should get the same result, that our method which we are using in fmincon was also interior point. Okay, and what MetPower is using is also interior point. Okay, so some interior point. So this is a built-in linear solver, and the solution is converged. Converts in certain seconds. The function value. Then some system summary is provided. Okay, that how much is the total generation capacity. Reactive power limits are like, reactive power can supply or consume this much, and what are the different loads, branches, and everything is basically provided here. What are the different minimum, maximum limits, and everything is um, provided here. Now this is the information which we are looking at. So you can see the first bus has the power generation of 210. Are we also getting the same results or something else? Okay, so let's see. Uh, do we have the same results? Yes. This generator 1 and generator 2 are connected at bus 1. So 40 megawatt and 170 megawatt is basically, I think if you add those values, it is 200. Sorry, it is 210 value, right? So, so the first generation is 210. Reactive power is 68.93. So let's see, the reactive power is coming up something else here. Okay, so that is because some different solution. Whenever we are running this particular problem, some initialization is different, or some maybe the initial point is different, and it is a local minima. So from the reactive power point of view, the solution is different. But apart from that, if you see 151.68, 100.29, and 543.78 are the other generation values, and we are also getting the same values: 151, 100, and 543. Okay, if I look at the angles, it's first and fifth bus angle is 1.1, so we were also getting this. And sorry, magnitudes are were this, and then angle is like 2.622. So I will just compare the very first angle. So it is 2.622 is the same value. So yes, we are getting the same result except the reactive power. Okay, because every time, some as these are like non-convex, we may get different result. Okay, but the driving force was active power. So from active power point of view, we were getting the same results, and then voltage state of the system, we were getting the same voltage magnitudes and angle, and the lambdas are also exactly same. Okay, then the another information is like in Mat Power also provides this information, and if we are writing our code, we have to calculate these values once the results has been obtained. So these are basically like different power flows, and then you can see that like certain limits has been violated. It is saying that this was the minimum limit, maximum limit, and the values are this. So 150 and 1118 were the voltage maximum mu, and let's see. So upper limit was 150, and roughly around this value was here. Okay, so we can see it that the almost same dual variables are obtained here as well. So I will share this piece of code with you, and there is an assignment as well here. So like for if you want to include some inequality constants, you can put it 300 and try to solve it. That if I place a inequality or power flow limit of let's say line 1 2 equals to 300, what will be the answer? And to verify, you just simply place this 400 with the 300. Okay, and I can show you the answers that what will be the answer. So it is like let's say dt equals to load case 5. So this has been obtained dt dot branch, and the first branch 6 to 8 is equals to 300, let's say. Okay, so we have placed and then run opf dt. So if I run it, this power flow has been restricted to 300. Okay, earlier it was uh, more than 300, it was like 322. Now I have enforced a limit that okay, the first branch limit should be 300. So you can see that the power flow of this particular line 1 to the first branch is restricted to 300 megawatts only. So these are like 2.99. So with the sum tolerance band, it is 300. If you restrict certain lines, if line flows are being restricted, then the output will change, the incremental cost of the generators will change, two areas will be created along with that particular line, and you can see that the different lmps are basically lambdas are available here. So these are like nodal prices, and by looking at this you can okay wait. So by looking at these lambdas, you can say like earlier it was almost close. Everything was roughly around 190, 120, or 118. So everything was 190 plus minus 2. But now this has been changed because of the congestion. So network congestion appeared, and because of that you can see like 154, 146, so very high value, as well as 107 of very low value as well. So because of congestion, we are not able to schedule some cheaper generators, or different generators are being changed. So the output is power flows has been changing, and because of that, uh, the incremental cost of the entire system will increase. Any doubts in this particular part? I am happy to answer those doubts. I So, any doubts in this particular part, like how we can solve different problems, uh, mat power, and how to write some piece of code in MATLAB? Good. So, how to develop these levels of proficiency in MATLAB coding? Practice. That's it. To be very honest, I have not written new codes since I think 3 4 years. Okay, so all of this programming is, I think, when I did my PhD. At that time, I've written lot of codes. Uh, if Yanga, you can unmute yourself. Okay, so while like if you are doing your PhDs, so the thing is, like it's not about programming. I don't like that you should learn the programming, and like if certain tools are there, and if you are able to get a solution out of those particular tools, I would recommend using those tools. Okay, don't have to basically uh, write down a very difficult piece of code. Like uh, if I have to just get the ACOPF solution, I would not recommend you write ACOPF code for yourself. Met Power is providing our these solutions, and they are editable as well. Like we can play with these Met Power codes. They allow it as well. It's not like it's illegal. They allow that. Okay, you can play around these codes. They are not some software, and everything is like hidden behind the curtain. It's all the files are like .m files, MATLAB m files, and you can see each and every file what kind of code is being written there, so you can edit and update those codes as well, like at your own. So I would recommend for ACOPF, DCOPF, do not write your own code. These are the like just basic fundamental blocks, like how we can build upon and write our own code for our other complex problems. Okay, and like for the classrooms, like if some students having some issues with that programming, we should know how basically the course has been working. The important part here is uh, looking at these attributes, like I explained to you like how the lambdas are, what is the significance of the dual variables, so that information should be available. uh, Yanga, if you have some doubts, you can ask.
Sir, you mentioned dynamic OPF, where time is also being maintained, means included as a variable.
So if
Yes,
time is included in the as a variable in the OPF, then it will be called a dynamic OPF. The time is also
sir.
part. So in that case, basically we are solving the OPF for 20. Let's say the time period is 24 hour. Like each hour we are solving. So we are solving the OPF for 24 hours. Uh, if there is no coupling between time A and time B, then you can solve it independently. Like instead of solving entire problem altogether, you can solve 24 different problems. But if some time coupling is there, and time coupling will come from ramp limits, if you are including ramp up and ramp down limits of the generators, then definitely those are dependent upon the time. Some minimum up and down time constraints if you are using, definitely those will also bring the time coupling. And sometimes what we do is we use energy storage in our system. So let's say like 5 bus system, at one particular bus we can include the energy storage. In energy storage, some energy will be stored at particular hour, then it will be released at some other particular hour. So time coupling is there. If time coupling is there, then we have to solve the entire problem altogether.
Yes. Another thing is how to include differential variables into
What
in the
what do you mean by differential variables? Like, what exactly is your like meaning?
so, equations that represent the dynamics of synchronous generators and like the swing equations. Uh,
Hmm.
Here, if the change in power in electrical and load that will be evolve with respect to time, like delta will evolve with respect to time. So that is represented in terms of differential equations and how to means actually I studied some paper where differential algebraic problem are being considered in that problem, that particular problem.
So, like with in those papers, were differential equations included in optimization as well?
Yes, sir. Like x ut means x means x dot is taken as f of xu, then
Hmm.
the x is evolving with respect to time, while u is the algebraic, z is the algebraic variable, so we can take the algebraic components, and u is the control variables like binary variables or uh, integer variables that we can take. So I was quite means, not able to understand how to include the differential algebraic equations in.
So, it is again some mathematical equation, right?
Okay, sir.
And
Yes, sir.
we have, like, so there are two things rightly mentioned by Satya Narayanan as well. Like, there is a question: is OPF kind of studies come in steady state or transient state?
It's
So,
steady state. I think. Means
yes.
transient state would be in dynamic OPF that
Yes.
you have mentioned.
No, dynamic OPF is not transient or dynamics of the power system. Let me tell you, it's a
Okay, sir.
very big difference. Um, so, we have different states in power system. One is transient, then we have dynamics. Okay, not dynamic. I'm calling dynamics. Okay, power system dynamics. I think the subject which we refer for that, and then we have steady state. Okay, so optimal power flow problem is a steady state problem. And what you are asking is basically incorporating optimal power flow with the system dynamics.
Yes, sir.
Okay, so those equations you were talking about, like, steady state, the state space equations, I think x dot,
Yes, sir.
like first order x, ax equals to, sorry, x dot equals to a, and that state transition matrix like ax plus b u, those kind of state
Yes,
transition matrix, I think, right?
yes, sir.
State space equations. So you are trying to mixing, like, the dynamics and the steady state solution. So OPF is actually was developed for the steady state analysis. Okay, and we are not looking here like how the voltage will behave if a transition is happening from a particular power to another power.
Yes,
Okay, so those kind of studies, yes, you can incorporate, it's a mathematics, but to be very honest, I have never like, tried to go into a dynamics of the system. Like, I always worked on the steady state because my area is, more towards economics, where I try to solve the economics and markets and prices related aspects of the entire power system. So how you can handle that with the dynamics, it is, yes, it may be challenging, but you have to
the
read
net
about it.
the net power must be using this dynamics. Na, means the time steps would be very small to solve. No, okay, sir.
So you are confused with the simulation and like, optimization.
Yes, sir.
So that timestamps are basically like just simulation how with respect to time as particular signal is behaving. That is the dynamics of the signal. And dynamic OPF is something else again, like for that entire 24 hours we are solving the optimal power flow, then we call it dynamic OPF, not dynamics of OPF. One thing, dynamic OPF is like time dependent OPF, we can say. And still uh, it is a steady state problem. It's not at all dynamics problem, because for a time period we assume that everything is at steady state. Okay, so we
Yes, sir.
assume either 15-minute interval or 30-minute interval or 1 hour interval. And for those 15 minutes, we assume that the load is constant. Like here in this particular problem, we consider that load is fixed. It does not allow it to, changing with respect to time.
Sir, another about it. Actually, the second order cone relaxation for OPF is there. Sir, why
Yes.
that is being used? Means
So
I get one second.
there are different relaxation techniques are obviously there. SOCP, second order conic programming. Some SDP is also there.
STP is
Some McCormick
maximum.
relaxations are also there. Okay, so those relaxations are to so if I try to solve whatever the very fundamental OPF problem I have given to you, I will not look for the relaxation of those. It can be solved, and you can see very simple piece of code we were able to solve it. But if you are going into the distribution, as I explained you, there are many different complex problems, and there we basically go for the current, current carrying capacity, and current will be again like square of some variable. So sometimes to make a system easily solvable and to look for the global optimal solution, we relax certain problems. So we will try to reduce the non-linearity in the system. So those relaxations are basically to reduce the non-linearity.
Yes, sir.
Okay, those kind of SOCP and SDP, these are used, even McCormick relaxation, and there are multiple others as well. Sometimes we divide the entire problem into two parts, and with the help of distributed optimization we try to solve it. Okay, so
Yes, sir.
just to remove the complexity, and once we solve it separately, some variables are fixed, and if some variables are fixed, then the entire problem becomes linear as well.
Yes, sir.
Okay, so from the solution ease and solution point of view, we do the relaxations. Okay,
Yes, sir. Thank you, sir.
yeah. So I hope we are basically the entire why I was discussing all of these is basically the importance of each and every factor matters, and how to entirely formulate your own problems, that is important, because whatever I'm teaching, yeah, this is very fundamental and well established, but how to look at the your problems is important. Okay, so whenever you are trying to solve it, look at from the different perspectives. Apart from that, we will next week onwards we will move to the nature inspired algorithms as well, and we will try to solve them. Okay, and I will give you the very fundamentals, like how we can use the nature inspired algorithms, and how to very fundamentals of like few algorithms we will discuss in detail. uh, One more thing which I want to explain is tomorrow there is a sessions 10 to 11, and 10 to 11 I am, yes, I'm not muted. So yes, sorry. The tomorrow session is before lunch is 3 hour session, 10 to 1, And in timetable we have given it is like 2 to 4, but we will keep it 3 to 5. Okay, so some issue is there, like between 2 to 3 I will not be available, so we will keep it 3 to 5. And then Sunday there will be a quiz. It will be open for the entire day. Okay, and but you will only get 30 minutes. So make sure whenever you are free with a decent internet connection, then only open it. And once it's started, it will be finished within 30 minutes. But you can give that quiz at any time in the entire day. On Sunday it will be open, and then on Monday onwards we will start again. So about the nature inspired algorithms. Now we have still time, so this part is done. If let me see if I'm missing, I want to explain some other thing. So let's go and discuss games as well. So this is a software, and it have many solvers basically. So a lot of solvers are available in this particular. So it's if I say it, the full form is basically Journal Algebraic Modeling System, GAMS, and it has basically certain syntax. Okay, certain syntax are there and how to model a problem. So if you see in MATLAB, basically we were trying to uh, model our problem, and we have to build those these matrices with our programmable logic. So we have to build those matrices, and visualizing it for a very moderate size, like we can easily see that for 6 bus system it was, we were able to see the entire matrix, and like what is a matrix and what will be b matrix, and we were able to visualize it, so that like a programming logic can be developed to solve with fmin cone, or let's say quad probe or len probe. But as the system size grows, those matrix sizes will also grow, and in that case, sometimes like finding up or coming up with the proper logic is difficult. If some error is like in if some error in the logic, it is very difficult to find it out. So usually, like if very large piece of program or problem is problem size is very large, where a lot of variables are there, I prefer like my preference will be games. But the issue is MATLAB we have access to, so that's why we were discussing MATLAB. And games comes with like a license, and you have to purchase it. Most of our institutes or organization have MATLAB access, but GAMS, like you have to purchase it separately. And so we have like this license here at MNIT Jaipur. So I've been using it, and the problems which has been which we are writing in games is very, like it follows certain procedure. Obviously it has its own syntax, but writing the mathematics does not need any logic. It's the way we are writing in our like with notepad, the same way we can write the entire equation in games as well. So it's basically a modeling tool for mathematical programming and optimization. The one good or major advantage of this tool is basically uh, with mixed integer problems and non-linear problems, the solution which our fmin cone, or like the programmable the programming will give uh, will be some local minima, and it is very difficult to model as well. But here it is very simple. It based upon the problem nature. Sometimes the this tool itself select a default solvers. So it has lot of solvers available in the games library, and then it solves take those solvers and try to get the answer. If we can also change the different solvers, and by different solvers we can get like, let's say if some local minima or multiple solutions are there, then we can get those solutions. So depending upon like nature of the problem, we can opt different solvers. That options to different solvers is very limited with MATLAB inbuilt tools, but in games there are roughly around, I think, 20 or 30 solvers are there. Okay, depending upon different type of problems. So it can be used to solve different types of problem, whether it is linear, non-linear, mixed integer kind of problem. So we can solve those problems very easily here. The model is almost concise, and it makes full use of the elegance of mathematical representation. So like the way we are writing in our notepad, the same way we can write it in the games as well. So it's basically use the similar structure it uses. um, Data can be entered in most elemental form, and the model is portable and can be sold on different computers. So this is the structure of the model in the games. So these are the different things which we have to take care of it. So one is sets. So l- unlike matrices, uh, mat- games works in set theory. Like different sets will be defined, and that I also provided here. Like you can see, I have defined the set, like this entire equation in the ACOPF. I have defined that all of I are set of n. So I have defined a capital N as a set, and this n represents the set of number of nodes. So that's why I kept it here. Like we are going to use these in the for modeling of this ACOPF in games. So like set of generators is defined as a capital G. Then set of lines I have defined as a capital L. So this games works in like, so we have to define different sets in the games. So sets are used to define the index in the algebraic representation of model. So like set of generating units, sets of buses, set of slack buses, set of time periods, and etc. Like you can define a lot of sets. Then input data, so we have to provide certain input data. So whatever is the constants, we will provide that to in the system. So first we will define sets. Based upon those sets, we will provide certain input data. Those data can be either like single value, so scalars are there, and these can also be defined like number of generators can have different like uh, minimum limit and maximum limit. So let's say if we have set of generators, based upon that, uh, just a second, Roshan. So based upon those generators, we can provide certain input data. So those can be parameters or tables. Okay, so this is defined over the sets. Okay, then variables are basically the decision sets and are unknown. So we have to define that. Okay, these are my variables. So we have defined that in MATLAB as well, that what are the different variables. Then equations. So just like like the equations which we have defined in our MATLAB. So in MATLAB we defined that some constants are equality, some constants are inequality. So we have to provide all the equality constants with like all together, all the inequality constants all together, and that too like linear ones separately, and if non-linear are there, then in F-min cone they will be provided with C and C EQ, A EQ, B EQ, and A and B. So there were like if we go with the same logic in F-min cone, we can provide three kind of equations, like equality, linear, non-linear, inequality, linear, and non-linear. Okay, so equations are basically in games, you don't have to worry about whether the equation is linear or non-linear. You don't have to define them separately. and I will define it just like uh, this particular sequence I will use, irrespective of whether like this first two are non-linear, then some linear limits are there, then some non-linear equations. So irrespective of that, I can like basically choose any sequence, and whatever I have written with my copy and pen, whatever the problem I have defined, I can define those equations exactly the same. Okay. So like equations will be there, then these model and outputs are like hardly like one or two line. So but games gives us like freedom to define many number of equations. So we can define let's say 10 equations, and we can then create a models that okay, if this is my objective, and like out of 10 only keep the 5 equations altogether and solve it. So we can model and solve statements will be there, and in which we will like whatever the number of equations we have defined and the variable we have defined, we can basically create a model, mathematical model, uh, either considering all the variables and all the equations, or considering a few equations as well. Like we can remove certain equation that okay, we don't need this, we have kept it there to solve it for some other model. So we can have different models we can create, and we can solve the different models altogether in the games. Then output is basically there are several ways to see the output of the, like we can export it to our xls files and display them. And we can like excel files can be like all the data can be exported to the excel file. It can be displayed there as well. So these are the like fewer five or six elements like which we have to define in a games model. So with the help of these, we can define. Now, this is the overall structure of the games. So first of all, we have to define sets. So in the sets, we have some certain declaration. Declaration is basically user input, so I can provide any declaration there. It has nothing to do with the syntax of the games. It will not affect any solution. So like let's say if I have given that set I, and the declaration is set of generators. So instead of set of generators, I can say I can write any gibberish as well, like randomly typing anything. It does not matter at all. Then assignment of the members. So in each set I have to provide some members. So members, there are lot of ways to provide the members, and that will be so once you provide certain members, you give them some name, and those will be used throughout, like providing for the second step is like providing input data and declaration of the variable. So those sets at the members of the set will be used further. So that will create a problem if you define everything randomly. So we will have certain logic to define that members. Then input data, again the declaration part is always um, user input. He can write as many words he can he want to understand that okay, what input data set variable or equation means. So we can give this declaration. This is also optional as well, like if you do not provide any declaration, that is also fine. Okay. So this is how the structure of the games model will look like. And finally, like the once we have defined the input data, all the variables we have declared, then some bounds, and we will restrict the entire problem with certain equations, and then we will model and solve that particular equation. This is how the game's structure look like. Okay. So uh, this part I think we will continue in the next session, not today. If you have any doubts so far, I'm happy to answer those doubts. Otherwise, I think for today we will stop, and we will resume, I think, tomorrow at 10 Saturday. Thank you. If you have any doubts, you can put them in the chat box, or you can raise your hand. We will unmute you. Maybe many of you are, like not able to get the access of the games. Uh, if you visit MNIT, we can provide that in our lab. It is like the license is available in our lab, so um, like you can visit us, and you can try your code here as well. Like you can feel contact me as well, uh, if you do not have access to the games. So like you can install the demo version to so demo version is also like has all the features which a licensed one have, but the limitation is on the like how many number of variables you can include in that demo version, and the number of equations. So that is a limitation. With the paid license version, we don't have that limitation, so thousands of variables we basically solve for. So yes, if you can like build your own code, and if you just want to uh, run it, you can run it here. So you can, on demo version, you can write your own code, and you can visit us in our institute as well, and we are happy to help you if you do not have like the licensed one, or the license for the games. Okay, so if there is no question, we will wind up the today's session, and we will resume tomorrow at 10. So thank you.